Hello friends, and welcome to yet another lecture on Cape Open Flowsheet Environment. In this lecture, we will learn how to manufacture ammonia synthesis gas. As you all are aware that ammonia synthesis gas is a mixture of nitrogen and hydrogen in the ratio of 1 is to 3. Now 1 is to 3 is the molar ratio, that is for every 1 mole of nitrogen we have 3 moles of hydrogen and we get 2 moles of ammonia. Now, here we have the flow sheet of this process. As we can see in this flow sheet, I'll adjust it. The natural gas mixes with steam and enters the primary reformer. Now, the out gases from the primary reformer, they mix with air and they go into the secondary reformer. In the secondary reformer, the reaction is performed and then this is followed by a high temperature shift, which is then followed by a low temperature shift. Now, as you can see here, our starting source is natural gas. Any carbonaceous source, any source or any compound which has carbon can be used to produce synthesis gas. If we do not wish to use natural gas, we can use coal also to produce synthesis gas, and there are a few ammonia plants in this world which use coal as the starting material. But over the years, most of the countries have shifted to natural gas because natural gas is clean. There is no particulate matter in it and therefore the process is quite clean. So natural gas is the preferred starting material or carbonaceous source for producing synthesis gas. Now, in this entire flow sheet, reactions are happening. Now, what are the reactions? If you go to see in this entire flow sheet, 3 reactions occur. First is the methane reforming reaction, which is nothing but methane reacting with steam to give you carbon monoxide and hydrogen. Then you have the water gas shift reaction, which practically occurs in all the reactors, which is carbon monoxide and water or steam gives you carbon dioxide and hydrogen. Now you have the third reaction, which is the combustion reaction. In the combustion reaction, methane reacts with oxygen to give you 4H2O and 2CO. Now remember one thing, that this happens because there is an insufficient amount of oxygen. The oxygen required for complete combustion is not there. And therefore, what happens is you have a carbon monoxide being produced here. Now, in the primary reformer, methane reforming reaction and water gas shift reaction occur. And in the secondary reformer, since air is being pumped in, the combustion reaction also occurs. Now, here the interesting fact in this production of this synthesis gas is the quantity of air is controlled in such a way that we get a ratio of nitrogen to hydrogen as 1 is to 3. So, a measured quantity of air needs to be put in, because if we put excess amount of air, complete combustion would occur, fine, that is one thing, but you would get excess of nitrogen also. Now, how do we simulate this process in COFE? Now, in Cape Open Flowsheet Environment or COFE Simulator as it is known as, you have to configure the thermodynamic package and the reaction package to start the simulation. That's the first requirement. Therefore, configuring it, so we go to settings and we go to property packages and we click add and we select TEA and here we select new and I will give it a name, simulation for ammonia synthesis as the name, and I'll leave the description, but you can go ahead and give a description of your liking. Then we select Peng-Robinson equation of state as the model set. Now we add our compounds. The first compound, of course, is methane. This is followed by addition of water. Now this is followed by addition of carbon monoxide. Then we have carbon dioxide. Since we are adding air too, we have nitrogen. Which is followed by oxygen. And finally, as we can see, we have argon 2 coming in. So what we have is argon. So we have methane, water, carbon monoxide, carbon dioxide, nitrogen, oxygen, argon, and finally we add hydrogen also, because this is one of the products. So can we move it? No, we can't move it. So the hydrogen remains at the end. That's not a big problem. Let's click OK. And we assign this property package. Now we go to the reaction packages. In the reaction package, we click add and we select corn and we give it a name. Same simulation of ammonia I would like to give it 1 in case there is any problem with clash, because I may have put this property package earlier. Then we go to the compounds. Now we click add. So there are two ways of doing it. If we click add, we can say from material database, or from material template. So we select material template and we select all the compounds. Now, what is not reacting? We know that argon is not a reacting compound, so we do not select argon and we click OK. Now we go to the reactions and we create the reactions. So the first reaction that we are going to have is methane reacting with steam. So here we give the stoichiometric coefficients for methane as -1 and water as -1 to give us carbon monoxide and 3 hydrogen. So to give us carbon monoxide and 3 times hydrogen. Now this is an equilibrium reaction, so we click equilibrium and the phase for this reaction obviously is vapor. Now we again click create to write the second reaction. The second reaction is the water gas shift reaction, which is carbon monoxide plus steam, carbon monoxide and steam, that is water, gives you carbon dioxide and hydrogen. This too is a reversible reaction and it occurs in vapor phase. We click create and we enter the third reaction. Now the third reaction is the combustion of methane. So we have 2 moles of methane reacting with 3 moles of oxygen. To give you 4 moles of steam or water. and 2 moles of carbon monoxide. Okay, and this reaction is vapor phase 2, and we click OK. Now we are all set. It is always suggested that once you are done with setting the thermodynamics and the reaction packages, we save the flow sheet. So I click Save As and I click Ammonia Simulation Synthesis Gas and click Save. Now we start constructing our flow sheet. We have natural gas mixing with steam and the resultant mixture entering the primary reformer. So we first draw a steam stream. So for this, hold on guys. Let us check whether our property packages are done. Yeah, they are quite done. So we go to insert. Now, just a moment, I'll restart it. Yeah. Now we click and draw the first stream and we name it as stream number 1. So let the name remain as stream number 1 and we'll remind ourselves constantly that the stream number 1 is the synthesis gas stream. And then we have stream number 2, which is nothing but steam, and they mix. So we go to the select unit operations and we go to the mixers and we select a mixer and put it. And we name it as mixer 1. We leave the name as mixer number 1. We connect it to mixer number 1. We connect the streams. So we connect the stream to inlet number 2, the natural gas to inlet number 1, and the outlet from the mixer is drawn. So this is stream number 3. Now we go ahead and we put the values in the stream. So the pressure at which the natural gas is coming is 39.22 bar. So we double click on the stream and we change the units to bars and we change the temperature units to Celsius. So the pressure at which it is coming is 39.22 bar. We enter that. The temperature at which it is entering is 390 degrees Celsius. So we put it 390 degrees Celsius and we start with the flows. So the unit of the flow is of course kilomole and R. So we adjust the units, kilomole and R. Now the amount of methane flowing in is 1250 kilomole an hour. The amount of carbon dioxide in that is 3 kilomole an hour. And the amount of argon in that is 1.477. So let's check it. 1.443. So let's correct that off. 1.443. So we have entered all the information that is required. Now we go to the second stream, that is steam. Now steam here too enters at 39.22 bar. Now the temperature of the stream is an assumed temperature. So we assume it as 290 degrees Celsius. This is an assumption that we do. And the water in this is, so the amount of steam that is flowing in is 3750. 3750. That's done. And we click this button to simulate it off. As we find here that it is a vapor phase, but the outlet is at 317.922 degrees Celsius. Now the inlet to the primary reformer should be at 550 degrees Celsius. Therefore, we will have to increase the temperature of the steam. So, let us select a temperature as 632 and let's resimulate it and see whether we get the correct figures. So, we get it as 550.526. So, 622 or 632 would be a good assumption, and 550 is the outlet. Now, this stream number 3 enters the primary reformer. Now, to simulate the primary reformer, let's go to reactors and let's take a Gibbs reactor and select it and put it in this flow sheet. So, we take stream number 3 and take it as an inlet to the Gibbs reactor. Now, we rename this Gibbs reactor as primary reformer. And then we take the outlet stream. So, the outlet to this is of the primary reformer is 4. Now, we double click and go to edit. The outlet of the primary reformer is at 790 degrees Celsius. So, the operation temperature, we change the units here and we put it as 790 degrees Celsius. Now, we click edit once again here and the reactions we select as the reactions will be getting defined by the reaction package. And now we come to the pressure drop. Now, the pressure drop here is taken as this is 39.22 and this is 35.290. So, let's take a calculator. We have 39.22 minus 35.290 and the pressure drop is 3.93 bar. So, we again close this window, go to this window, select bar and put the pressure drop. Now, we again click edit and here we come. Now, the reactions that happen here is in the primary reformer, you have the methane reforming and the water gas shift reactions occurring. So, we click add and we select reaction number 1 and reaction number 2. It's done and we run to simulate. Now, we do get a warning here. I'll explain you the warning. Okay, so let's check this. Now, the outlet is at 790 degrees Celsius, 515. Obviously, methane has reacted, and we have carbon monoxide and carbon dioxide produced, and we have hydrogen being produced too. Now, as you can see here, in the secondary reformer, what happens is the outlet from the primary reformer is mixed with air, and this goes to the secondary reformer. Now, for all reactors from that is secondary reformer, HTS and LTS, I take the pressure drop as 0.5 bar instead of 1 bar for simulation. And for all the exchangers, I will take a pressure drop of 0.1 bar. So, let's go ahead and add a stream. So, we add a air stream. Now, we rename it as 5. Now, we take a mixer here After placing the mixture, we draw the outlet. And we name this as mixer 2. Now the flow rate of stream number 5 is, it is at 35.290 bar, and the temperature is 600 degrees Celsius. And what we do is, to start with, we put a flow of 1 kilomole an hour here, and the amount of nitrogen is 79.79, and the amount of oxygen is 0.21. We fix this ratio. After that, we just make a note. There's argon also entering in. So what we do here is, we enter the flow rates. That is 1349.150, 1349.150, and 362.9, 362.9, and we see here that the ratio has come roughly to 0.79 and 0.21. Now we also enter the argon flow rate, 17.280. So that's 17.280. Click. And now we are done with the flow rate of air. Now we run the simulation to get the output of mixer number 2. And there we have got the output of mixer number 2. Now this is at a temperature of 755. So now what we do is, a shorter way of doing things is, let's copy the primary reformer and paste it. The primary and the secondary reformer are more or less the same. So I can add a root point here to bend the stream. So add a root point, take this, bend the stream, connect it, and draw the outlet of this. Now I rename these streams. I take this as stream number 6, and I take this as stream number 7. Now I take the name and I rename it as secondary reformer. Now I go and configure this reformer. Now the outlet temperature of this reformer is 1000 degrees Celsius, as we can see here, and the pressure drop is 0.5 bar. So we adjust the pressure drop to 0.5 bar, and the outlet temperature we adjust it to 1000 degrees Celsius. And now we go to edit, and in the edit we go and delete the reactions first. Now again we add the reactions, as we know that all the 3 reactions are going to occur, so we add them. We are done. Now let's run the simulation. We are done running the simulation. Let's check what is the condition of stream number 7. The stream number 7 is at a temperature of 1000 degrees Celsius, and as we can see here, the amount of oxygen here is just 0. So all the oxygen has been consumed in burning up the methane, and there's very little amount of methane flow that is coming here. That is 0.0021% of methane is actually coming out. Now we can see here that the ratio of nitrogen and hydrogen is not to our liking. This value should be somewhere around 4200. That ratio, that correct ratio of hydrogen is achieved by using shift reactors. So what we do now is, the shift reactor is going to be similar to the primary and the secondary reformer, but the only difference is it is going to have one reaction. And also the stream number 7, when it enters the stream shift reactor, is going to cool down. It's going to enter at 350 degrees Celsius. So we will have to cool it down. For this, we will have to place a exchanger which will raise steam. So we go to our unit operations, select heater coolers and place it. Rename this as steam generator. Okay. And draw an outlet to this. Rename the outlet as 8. Now double click on the steam generator, go on edit and select outlet temperature. Close it. Change the units. So that's 350 degrees Celsius. And the pressure drop is 0.5 bar. Sorry, 0.1 bar. 0.1 bar. Now we run the simulation. So this is at 350. Now we copy the reactor. Now this is our low temperature shift. So first I go about renaming it. That's high temperature shift, not low temperature shift. So HTS. Take this stream, add a root point and connect it to the reactor. Draw an outlet to this high temperature steam. Rename this stream as 9. Now double click on this reactor. The outlet from the high temperature shift is at 420 degrees Celsius and the pressure drop is 0.1 bar, 0.5 bar. So 0.5 and the outlet is at 420. So we enter the temperature and we click edit, go to reactions and we remove the reactions that are not occurring in the reactor. And we run the simulation. Now as we can see here, the amount of hydrogen has increased. So this is the purpose of the shift reactor. The shift reactor takes carbon monoxide and along with steam, it generates carbon dioxide and hydrogen. Now, as we can see here, the ratio is not quite up to our liking. So we add another shift reactor, which is the low temperature shift reactor. First, we have to cool down the stream. We copy the exchanger for this. Place it here. Rename this as steam generator 2. Connect its outlet stream. And the outlet temperature to this is going to be 200 degrees Celsius. So this comes out at 420 but enters at 200. So 200 degrees Celsius. And that's it, we are done. The pressure drop is 0.1 bar. and we run the simulation. Now we copy the low temperature, high temperature shift reactor. Because the low temperature shift reactor is similar to the high temperature shift reactor. So we can merely copy it and reuse, add a root point, connect it, draw the outlet and rename this to low temperature shift. Now we double click on this reactor and we do the simulation, isothermal simulation of this reactor at 220 degrees Celsius. So we enter the temperature as 220 and the rest remains as it is and we run it. Double clicking on stream number 11, what do we find now? Let's go to the calculator. There we are. The amount of hydrogen is 4181.54. So 4181.5454 divided by the amount of nitrogen, that is 1349.15. And there we are. The ratio of nitrogen to hydrogen is 1:3. The hydrogen is very slightly in excess, and that's required. So as you can see here, you have seen through this simulation what is the exact purpose of putting the shift reactors. That is to increase the amount of hydrogen. Now what we find here also is that we have argon and we have carbon monoxide and we have carbon dioxide. Now the amount of carbon monoxide that we have is 0.00192 and we have a carbon dioxide in this and we have methane too. Now the synthesis gas that actually goes to the ammonia reactor has very little amount of carbon dioxide in it. It mostly consists of very little carbon monoxide and carbon dioxide. Why? Because carbon monoxide is a poison to the catalyst. So it has to be in very minimal quantities, very close to zero. Now carbon dioxide is one of the inerts that we cannot remove fully. So this unit operation of low temperature shift reaction is followed by removal of carbon dioxide. Now for this we have an amine system. Now after the amine system, the stream goes to a methanation reactor where the carbon dioxide and the carbon monoxide are converted to methane. So what we have here is that the stream that finally leaves the methanation reactor, it has very less amount of carbon monoxide and carbon dioxide and a rich amount of nitrogen and hydrogen and very less amount of argon in it. And a very little amount of water too. So how do we simulate for these unit operations, that is removal of carbon dioxide and the methanation reaction or the reactor? I leave that to you as an exercise. Attempt it and do write the results in the comment. If you need any guidance, write in the comment. But before that, like and subscribe my videos. That is very important. That motivates me to make such videos for students and professionals. Now let's go to the warnings. Let's accept all the warnings. So here we are done with the simulation. Now, if you want to look at the results at a glance, the best way is to go to Insert, go to Stream Report, click, select all the streams, place them here and click OK. Now, as you can find here, we get a stream report here, and where we can see that the stream number 11 is at a pressure of 33.59 bar, is at a temperature of 220 degrees Celsius. The flow rate is 8,833, and the oxygen in this is 0, and it has the right amounts of nitrogen and hydrogen ratio. That was all about the simulation for synthesis gas. Once again, do like and subscribe my videos and put your comments freely so that I come to know if you have any doubts. Have a great day. Goodbye.